All right, it's a few minutes after, so I think we can get started. So today we will be hearing from Lee McCuller. Lee did his work at the University of Chicago, where his thesis was on testing a model of Planck scale quantum gravity with broadband correlation of co-located 40-meter interferometers. He then moved on to MIT as a postdoc and then later as a research scientist, where he worked on the LIGO experiment with specific focus on implementing frequency-dependent squeezing in the LIGO experiment. And I believe today his talk will be touching on that work. And with that, thank you, Lee, for coming, and feel free to take it away.
All right, yeah, thank you for the introduction. So today I want to talk about LIGO, introduce you a little bit to the LIGO experiment and what we're doing with quantum optics to improve the detector and improve the science output and astrophysics reach of the instrument. So to get started, these two kind of cool pictures are our primary motivations of this experiment. On the left is our optical parametric amplifier that produces squeeze states, and on our right is a view of one of our test mass mirrors, what the physical object that is used to detect gravitational waves. And the question is, how strongly and what are the consequences of probing the position of these 40-kilogram test masses at the level of precision that LIGO does? And but to motivate that, what is LIGO? What is gravitational wave interferometry? So historically, the field of astronomy and astrophysics has been driven by observations using electromagnetic waves, pointing a telescope at the sky and seeing what is out there, probing for new objects, which imply new populations, new formation methods, and all of the various kinds of physics that drive the dynamics that you see out in the sky, in the cosmos. And of course, every time a new optical wavelength, new technology has enabled a new view of the universe, which probes new objects, new populations, and the new physics behind those objects. So this is just a view of the skies and the various wavelengths that telescopes can now view. But now, these days, we are moving beyond just electromagnetic observations to new modalities of physics, new kinds of ways of observing the cosmos using things other than electromagnetic waves, such as neutrinos, high energy cosmic rays, and ultra high energy gamma rays, and of course, gravitational waves. And because they are different modalities of physics, they're kind of sensitive to very different objects in many cases than electromagnetic waves. And when they are sensitive to the same objects, and you can see the same object with both telescopes and with these new modalities, you get a very full and rich view of the physics and the objects that you can see. And this is the dawn of multi-messenger astrophysics, using multiple kinds of observatories at once. So I'll be talking about, in this case, the gravitational wave picture. And what do we view out from gravitational waves using these observatories? Well, we view so far just binary compact objects. These are things like black holes or neutron stars, which are small and dense enough that they can orbit extremely close at large fractions of the speed of light as their orbital velocity. And they're so massive that their rapid orbits actually produces waves that go into far field in space-time. And so these compact binary objects are hundreds of megaparsecs away. So a megaparsec's 3 light years approximately. So these are hundreds of millions of light years away, extremely distant. And of course, they're fascinating objects. So black holes are already an interesting, unusual thing that we historically haven't been able to see very many of, and often with rather indirect evidence. And now we see extremely direct evidence of not just single black holes, but pairs of them. And as they orbit and they collide, we see not only that they exist and that they're out there, but we see transients in space-time from the intermediate object that is coalescing from the merger of two binary black holes. And of course, neutron stars colliding has extremely rich physics because there's a lot of strong force and nuclear physics that goes into just the neutron star equation of state that you can probe very deeply based off of gravitational wave signatures of neutron stars. And of course, the very rich multi-messenger astronomy that occurs from all of the ejecta during the merger state. So what does it mean to measure gravitational waves? So, and what's a little bit of the history? Well, the basic idea is these compact objects stretch and squeeze space-time. If you have a sensitive enough measure of distances, then you can actually see that that the lengths that you measure are changing. And the idea that you could actually do this with a sensitive enough optical interferometer came from Ray Weiss at MIT. And of course, even if you have this idea, there's no point in building it unless you think that there are objects out there to see and that you will have signals that show up in the instrument. And a large piece of the science case, both the astronomy, what's the general rate that you might think, and what are the waveforms? What is it even that you see when two objects merge? Was driven by Kip Thorne at Caltech. And in our case, for LIGO, these detectors, how have they manifested in the US case at least, are 2 4-kilometer optical interferometer observatories, one in Livingston, Louisiana, and one in Hanford, Washington. These are aerial pictures. Of course, the third Nobel laureate for gravitational wave discovery is Barry Barish, who orchestrated and made these sites exist, made the program really become an experimental program as far as the facilities it requires to do this. And the 2 LIGO detectors or observatories are part of a gravitational wave network, a global network that at this time primarily includes Virgo, a European detector in Italy that's 3 kilometers. And historically in the initial LIGO, the first iterations of the gravitational wave detectors, a lot of technology development and early development came from the GEO 600 meter device. And there's a planning sort of at very early construction, a LIGO type device in India. And then there is a cryogenic detector in Japan, Kagra. And actually, Kagra should be considered operational. This is slightly out of date, although they're still increasing their sensitivity to useful astronomy ready levels. And so what do you see with these devices? Well, you see audio waveforms in gravity. And on the left, at least for the observing run 2, you can see a set of these that were observed. And of course, to you, they kind of look similar. They have similar features. But of course, each of these is a separate event. And even though this is a bit of a population, each one is made up of individuals. Some are the highest mass ratio, some are the spinniest, some are the highest mass, and particularly in some unique mass ranges that are otherwise difficult to observe or you would think should be excluded. Some of these have now been seen in gravitational waves. And of course, here is a binary neutron star that started multi-messenger astrophysics. And then on the right, you can see how this has grown in the next observing run 3 that recently ended. And the number has just increased dramatically in terms of events that have been seen. So what does it mean to see a gravitational wave? So on the left is still one of my favorite plots from the first detection of binary black holes and gravitational waves for that matter. And 2 compact objects are orbiting. They have extremely small radii, so they can orbit very close. On the bottom here is their velocity, large fractions of the speed of light, which is remarkable for, in this case, 30 solar mass black holes. The gravitational wave that they emit is a quadrupole wave in the metric that goes, in this case, about 1 billion light years to Earth. It sort of travels being a quadrupole wave. It kind of has this tube shape that passes into the Earth. And as it does so, in one direction, ignoring polarization here for a moment, in one direction, the arm of an interferometer expands, gets longer, and the other one gets shorter. And this is exactly the signature that a Michelson interferometer reads out. And as the wave passes, the lengthening and shortening alternates. And so this is great because you don't need to know the absolute distance of these arms. You just need to see them modulate at some frequency that's characteristic of the gravitational wave. So that's a useful thing in that you need a very precise instrument, not necessarily an incredibly accurate instrument. And as the wave evolves due to the system emitting gravitational radiation, that causes its orbit to decay through the loss of energy. And by decaying, the two objects get close together. They, in fact, their velocity increases, which increases the rate of energy emission until it hits a singularity where they sort of chirp. The chirp is from the increasing velocity, and then they touch. And this is this merger and ring down phase here that you can, in the data is actually very difficult to distinguish this, but you can see up to the merger. Ring down is challenging still. And what are the figures of merit for a gravitational wave detector? I'll go through the three major ones. The first is just the strain noise spectrum. So the interferometers measure a gravitational wave time series. They measure this strain modulation as a function of time, even though it's often easiest to talk about it in the frequency domain. And so this is given in a plot such as this, which is in the strain amplitude spectral density. So this is in some sense meters of displacement sensitivity divided by meters of length of these 4 kilometer arms. And it gives a characteristic strain sensitivity of kind of a few 10 to the minus 24 per root hertz. Now this per root hertz is a strange unit. If you square it, you just get per hertz, and that is the strain variance as a density in frequency. So if you know kind of the band over which you're trying to detect something, you can multiply it by that bandwidth, and you get kind of the overall strain. Or in some cases, it's often useful to just think in terms of displacement, at least in terms of interferometers, and that would have units of meters or meters per root hertz. So the strain spectral density, when you apply like an exact template that you're searching for, you get an in-spiral range. That's the average distance out to which you can see certain classes of compact objects. The main fiducial is 1.4 solar mass binary neutron stars. And we can typically see those now out to about 140 megaparsecs, where 1 megaparsec is 3 million light years. And what's interesting is that the event rate that you see scales with the volume that you capture. So if you double the sensitivity of your detector, you increase the event rate by an order of magnitude, nearly by a factor of 8. And so the final one that I have is, if you actually take the spectral density and multiply it by a bandwidth, you get an RMS strain. This isn't actually a terribly useful figure of merit, except for a couple of points that I want to make as I talk. So in our case with this, if you multiply by the arm length, the strain spectral density, multiply by the band of 50 to 200 hertz, which is this kind of bucket as we call it, you get that we're measuring about 150 times per second at a level of 2 times 10 to the minus 19 meters. And that's remarkably precise. And it actually might start alarming you at how precise that is, because it seems like that shouldn't even be reasonable. And I'll talk about that in a moment. But in terms of just distance scales, the precision of LIGO is down here. It's actually even smaller than the electroweaker Higgs scale, although it's a very disingenuous comparison to put them on the same plot because the physics is entirely different. But measuring at this level allows you to see, because they're so massive and extreme of objects, binary black holes out to 1 gigaparsec, 10 to the 25 meters away. And one other remarkable thing is that this is about within a factor of 10 of the Hubble distance, the horizon, as far as you could even possibly see. And at the very end, I'll talk a little bit about, can we bridge that gap and actually see all of these events in the universe. But before I go into those two kind of things that I've hung out there, I just want to talk about what is, we'll be thinking about quantum noise as far as the interferometer goes and squeezing. But so what is the baseline quantum noise that you can consider for a Michelson interferometer? Well, if you have a single photon, it essentially can make a measurement that is its wavelength divided by 2 pi. In our case, that's 1064 nanometer light. Divided by 2 pi is about 10 to the minus 7 meters. And if you just have a lot of photons and they're in a coherent state, they're all making entirely independent measurements. So the sensitivity you get basically goes down to as 1 over the square root of the number of photons that you have counted in some interval. If you have a power and you're counting them at some rate, you can actually convert this into a spectral density and say that it's meters per root hertz or meters squared per hertz. And the main point is that there's about 10 to the 19 photons per second in 1 watt of light. And so that's an awful large number. And so even with 1 watt of light, you can get something like 10 to the minus 17 meters, which is a remarkable sensitivity. LIGO is, of course, about 3 orders of magnitude more sensitive than that, more precise than that. And to do that, we use a series of optical cavity tricks, both to increase the power from 1 watt to 1 megawatt. That 10 to the 6 more photons gives 10 to the 3 better sensitivity. And then we use the actual cavity effect itself to manipulate and trade off between sensitivity and bandwidth. And that's, the arm cavities both change the power level and the bandwidth. And then we use this signal recycling cavity here at the bottom to actually go the other direction and expand the bandwidth back out from what would otherwise be an excessive sensitivity. And I'll talk about why you can actually have an excessive sensitivity here in a moment. But to talk about the quantum noise, especially in the context of gravitational wave detectors and LIGO, it's not even meaningful unless you can build a device sensitive enough to reach that level of quantum noise. And LIGO is a triumph because it has combined a number of kinds of engineering to reach its quantum noise limit. And to name a few, it uses active inertial isolation with very precise seismometers that it moves 1-ton stages to be as inertially quiet as the seismometers themselves. It then uses quadruple pendulum suspensions to get 1/f to the 8 isolation, so that you can go from 10 to the minus 10 at 1 hertz down to 10 to the minus 18 meters by 10 hertz. For example, the actual thermal noise, the vibrating of atoms, due to this is an entirely room temperature detector, can and does limit the detector both from vibrating, materials in the optics. So we have specially designed optical coatings for coating thermal noise. And the final stage of suspension uses pulled glass fibers, which have a remarkably high Q, so very low internal mechanical losses. And they have a Q of 1 billion, which corresponds to a 2-week ring down. If there's an earthquake or something, it actually takes weeks for little lines in our spectrum to ring down. And of course, extremely high quality optics. All of these things have been necessary. And we have put them into this noise budget where the various contributions from seismic, going through all of this attenuation, such as the suspension, the brown curve, the remaining thermal noise from these few silica glass suspensions is in blue. Newtonian noise is actual gravitational noise from passing seismic waves and from air currents moving mass. And then this red one, which is highly limiting, is the coating thermal noise from the mechanical loss actually driving fluctuations of the wavefront surface in the mirrors. And then finally, what we'll be talking about is largely this purple curve, which is the quantum noise. But to preface the quantum noise, you see that it has a certain shape to it, high at low frequencies, and then it goes high again at high frequencies. So the high frequency roll up is because we use cavities, and that has a bandwidth associated with it. So our sensitivity is naturally decreasing, and that corresponds to an increase of noise at high frequencies. At low frequencies, what is this increase in noise? And in some sense, I want to point it out. I want to go kind of a circuitous route and say that it's a rather fundamental problem, this low frequency noise. So we measure the position of the test masses, let's say position X, and we measure them continuously in time. And we measure them at a rather absurd precision, 10 to the minus 19 meters, let's say. If you ignore units for a second, 10 to the minus 19 meters is smaller than the square root of H bar. So that means that fundamental uncertainty is following you around. And the way it plays out in this argument is that, let's say you measure X to this precision, and that means that you have imprinted a large momentum uncertainty onto your test masses because of the high measurement precision. And now you measure position again, well, that momentum is also velocity. It integrates up to be a system uncertainty sometime later. And so you now find yourself fundamentally limited. Your system uncertainty and your probe uncertainty, your actual measurement uncertainty is the quadrature sum of these two things. There is a optimal probe strength. There's an optimal level of sensitivity you should be measuring to. And it, of course, depends on the measurement time that you choose, how long this velocity gets to integrate up. And the fact that we're measuring continuously is why we have this low frequency spectrum. So you can convert everything from the time to the frequency domain and work out frequency domain versions of these things, and you get kind of this fundamental limit, what's called the SQL. Of course, there's many SQLs, so I'll call this the mechanical SQL. And it looks like this. So LIGO actually has a probe strength that for many frequencies below about 50 hertz, it is above the optimal probe strength. That's why it's rising up higher than the SQL. At some specific observation bandwidth, it is nearly touching the SQL. It's not exactly touching it because it's not perfectly efficient detector. But it's designed to be along and nearly saturate this fundamental uncertainty as best it can. And so, what can we do with that? Can we touch it? Can we get there? Can we manipulate it? The answer is actually we can do a lot of things. And what's interesting about this, it looks very fundamental given the argument I just gave, but interferometers are measuring this position using optical light. So light here must be responsible for whatever these noisy consequences are, this uncertainty, whatever wave function collapse, whatever you're calling it, that's driving this Heisenberg uncertainty principle. So it's the quantization of the optical light that's enforcing this uncertainty condition in the masses. And that's really quite remarkable. So the other way to look at this is simply radiation pressure noise. So these individual photons that make individual measurements in a Michelson, they each carry a tiny bit of momentum. They reflect off the mirror, so they cause some momentum transfer. And if they have their shot noise, they're sort of punching the mirror as they arrive on it. And that is driving up noise. That creates a force fluctuation. The force fluctuation integrates into displacement, and that it creates the phase fluctuation in the Michelson senses, and that masks gravitational waves. That's the other way of viewing this increase in noise at low frequencies. And this is kind of the breakdown. The 1/f² is this quantum radiation pressure noise, and then the going as f is the arm cavity bandwidth here. And as you increase the amount of power in the cavities, of course, you increase the radiation pressure noise, and that exactly corresponds with the increase of the probe strength, the arm power being more useful for high precision. So as you increase the power, you increase this probe strength, you do improve your precision at high frequencies, but you degrade it at low frequencies because you've sort of exceeded the optimal probe strength. But to go into further ways to think about this and manipulate it, I want to talk about squeezing. Squeezing is interesting because it is a different way to alter the probe strength. When you squeeze light, you are increasing the sensitivity. That's what's happening here in these plots. There's tests about 10 years ago where Geo 600 and LIGO independently attached squeezing systems to their interferometers and improved their sensitivity at high frequencies. And now for O3, we have done the same thing to improve the actual astrophysics output by improving the sensitivity of the detector. And what is squeezing? I can't go into all of the details for this talk, but Carlton Cave's paper from 1981 points out that actually a very subtle thing to think about, but even though the laser is coming in one port of an interferometer, it's the quantum state going in the output port and reflecting off of the interferometer that is responsible for the noise in the detector. Is by default, vacuum states go in. These vacuum states have equal uncertainty in both the amplitude and phase. They reflect off of the interferometer. They combine with the little bit of light leaking out that you use to detect motion, like that you use as the interferometric readout. And that's what causes the Poisson statistics, the shot noise in the detector. And so if you're looking for time domain signals and you have some variance, you're measuring in the phase quadrature, then the time domain signal is a displacement operation that moves around the mean value that you might detect, but the uncertainty is always there. So each realization of a measurement here would be random within this circle, and we only measure along the phase degree of freedom as we use what is a kind of homodyne readout in our Michelson detector. And so the point is that if you could change the default state from being a vacuum, having some default uncertainty in the phase quadrature, and you could lower that uncertainty, then you could win here. And that's exactly what we do using squeeze states. We trade off, we lower the uncertainty in the phase quadrature for increased uncertainty in the amplitude quadrature. And that, by lowering that variance, improves our precision. So the way we do this, just sort of broad physics overview is we create this kind of interaction vertex in our squeezer device. This B is a pump photon that is a frequency doubled photon in our case. And that, with some small interaction, can create photon pairs. That's this AA. And that's this emission process where you get photon pairs. What's interesting is that this Hamiltonian that people are maybe have seen in undergraduate texts or graduate texts on squeezing is only at a single frequency. But when you have a single pump photon, actually all frequencies of the red light come out in the pairs. So, and they're always correlated in frequency. And this is actually a useful thing in terms of LIGO. So this is the pair emission that corresponds to squeezing. When you have the interaction, you can also get up conversion or second harmonic generation. But what we actually use, or the process that creates the squeeze ellipse in the optical quadratures is down conversion. The fact that a virtual photon coming in, interacting with the pump, creates a virtual correlated photon. And upper and lower frequencies do this in a phase coherent process. When you convert from the sideband or the ladder operators to the quadrature operators or Hermitian operators, then you get a squeeze state. And it's a squeeze state at every frequency offset from the carrier. That's why I put these little stacks here, is that it will affect every individual frequency band in your noise spectrum. That's actually kind of remarkable. What does it physically look like? We use a crystal optical parametric amplifier. This uses a nonlinear crystal with a chi-square nonlinearity where the power level modulates the phase shift or the index of refraction through the crystal, and thereby, correlates the like when you have a modulation due to a pump photon at twice the frequency, that creates the interaction that can do frequency conversion that was in the previous slide. And we use cavity because that enhances the interaction strength quite a bit. We increase the power level of the pump using a resonance at the 532 nanometer wavelength. And then we also increase the interaction strength of the pair creation / squeezing operation by having a moderately high finesse of about 100 and at the 1064 wavelength. And we use this bow tie configuration because it's traveling wave, and that's good for technical reasons, backscatter, tiny bits of light that go back to the interferometer through the squeezer. This has been developed over the past decade. More than that, these squeezers. Ours is all done in vacuum, also for noise reasons, technical noise reasons. So we put this whole system in the vacuum chambers that LIGO uses. And so we did this in 03. This is the latest incarnation, one where we actually were using the observatories for astrophysics. 03, of course, saw many improvements that improved its sensitivity. The power level is increased, backscatter, or not just backscatter, but all manner of scattered light, where various things in the environment are moving, but they touch the light very slightly from just incoherent diffuse scatter off of the optics, even though they're extremely high quality. This all couples in noise. The duty cycle is improved. Just electrical noise from grounding, 60 hertz. You can see the 60 hertz line was improved dramatically. So that cleaned up at low frequencies. Anyway, many of these things, which you can read about in this paper, were done to improve the detector. And it has led it to be extremely limited by its quantum noise floor. Also, its coding thermal noise. That's why it doesn't quite fit the quantum shape because of the coding thermal noise. And so now we can turn on squeezing and expect to see the sensitivity improve. And indeed, we did. The Livingston detector in this case went from 120 megaparsecs to 140. Doesn't seem like a huge relative increase, but again, when you convert that to volume, that's a 50% rate increase on top of all of the other improvements. And this plot down here at the bottom shows the impressive change in the event rate during the 03 run. So now going back to the, what is going on at low frequencies. Actually, I'll go back here. You can see that at low frequencies, actually the noise might even be increasing a little bit. It's difficult to see in this one. Actually, there are technical reasons for that. But As you increase squeezing, you're increasing the probe strength, you expect to be increasing the radiation pressure noise. And to get into why that happens and actually think more completely about it, we have to move off of the particle picture of individual photons punching the in mirrors and transferring momentum. We actually have to think of the optical state, the two quadratures of light, in a coherent manner. So when you have an amplitude fluctuation of the wave, yes, that creates a force displacement and then a phase shift. And the amplitude fluctuation is a fundamental has a fundamental quantum uncertainty to it. It's not just that it's shot noise, that it's individual photons, whatever that means. Inside of the interferometer, it's very much wave-like. I mean, that's the only way you get interference at a beam splitter. So, so when you think of it that way, this is simply a matrix that couples the amplitude quadrature, the A1 in this case, into the phase quadrature after the reflection off the mirror. And this K factor is it's unitless, but it mostly has the susceptibility of the mirror's mechanical transfer function, force to displacement. And then, yeah, it includes the conversions of amplitude to force and then displacement to phase in there. That's what makes it unitless. But interestingly, this is a shear operation. This matrix is shear, and shear internally is a squeezing matrix with a couple of other rotation matrices. So there's a nice way of viewing this, which shows you what is going on in terms of radiation pressure noise, where what's going in by default is a vacuum state that has equal uncertainty in both quadratures. And at low frequencies where the mirror has some susceptibility, where if you push with a force, it will integrate up into a displacement. At these low frequencies, the amplitude quadrature is shearing into the phase quadrature. Since we measure phase, this is the increase in uncertainty that is radiation pressure noise, is this exact process. And of course, if you turn your head, you say, hey, there's a squeeze state there. The interferometer is also, in fact, creating squeeze states through its optomechanical interaction. This is what's historically been called ponder motive squeezing. Now, if you inject squeeze states, yes, squeezing probes harder. You expect it through this very early uncertainty principle that you expect the sensitivity actually to degrade at low frequencies due to this. In this coherent optical quadrature picture, what's happening is that you've widened the state. When you shear that, it actually shears upwards to a much larger degree. And that is the sense in which squeezing increases radiation pressure noise. And so the question is, can we see that? And is it useful in any case? So me and a graduate student at MIT took data at Livingston using our new squeezer platform, where we first injected no squeezing, we just turned it off. And we got a baseline of the noise with a good model of the quantum noise contribution. So this is all noises in the interferometer. This is the quantum noise. You can subtract off the quantum noise to get all of the excess classical noises. So when you subtract off the quantum noise, it's not just the shot noise, you also subtract off the radiation pressure noise. This is all of the remaining noise in the detector, and it looks very much like just coding thermal noise in a large band and some excess, a variety of excess noises, which have been budgeted out at lower frequencies. Then Houtoun took our squeezer system and didn't inject the usual squeezing, didn't inject phase squeezing that improves the noise at most frequencies. She injected it at a peculiar frequency, 35 degrees here. And you see that the total noise of the interferometer has this peculiar shape. And you can see in particular that it dips rather noticeably at these low frequencies. And of course, it's degraded at the high frequencies. And if you then remove all of those classical noises, and of course, you take the measurements in a particular sequence so that you have a very high confidence that you're not over subtracting, you see what the quantum noise in particular has done. And you see that when you have injected this off angle squeeze state, the shear action of the radiation pressure noise simply unsqueezes. It doesn't increase, it actually just lowers the squeezing a little bit. And this, in our case, has allowed us to go below the standard quantum limit that I described earlier for a limited band of frequencies. And this is quite remarkable because at the beginning, it seems rather insurmountable that you should be able to surpass this measurement uncertainty, this Heisenberg uncertainty. But now it's apparent that indeed using a squeeze state, you can go and make observations with quantum noise below this mechanical SQL if you inject at particular frequencies. And remarkably, this shows that indeed the vacuum is pushing the mirrors, that radiation pressure is a real and strong quantum effect. It shows that it's not a limit. And that to do this, it means that these 40 kilogram optics are preserving the quantum state of the optical system that they are in contact with, that they're not somehow decohering it. This somewhat violates any notion that it could be like individual, photon punchings of the mirror or shot noise on the mirror, because that would seem to be a very incoherent process that wouldn't preserve this. And of course, doing this kind of sub-SQL measurement has been done before, but in LIGO's case, this is 1 billion times heavier than this has ever been done. And very human scale test masses and at room temperature. So the talk is wielding the quantum correlations. This here, I would say, is simply brandishing the quantum correlation, showing that indeed you can go below the sub-SQL, but we would like to improve astrophysics while we do it. And all it took was choosing a particular angle of squeeze state. So what you would really like to do is change the angle of the squeeze state as a function of frequency, so that you don't have a narrow band that is sub-SQL, you actually have a wide band over which you're gaining the benefits of squeezing. And so this is simply the technique we call frequency dependent squeezing. And the question is, can you manufacture these states? And the answer is yes. You can both manufacture them. There've been 4 now experiments that have done it at various frequency bands. Most recently, me at MIT, and then a group in Japan at the Tama experiment have created truly audio band sub 100 hertz frequency dependent squeeze states. And what you do is you use an optical cavity that is off of resonance, and this causes a differential effect on the upper and lower side bands, which are correlated by squeezing to rotate them differently at different frequencies. In our case, to have this 60 hertz rotation, we needed a 16-meter cavity with a finesse of 80,000. It's approximately a 100 hertz line width. The photon going back and forth in this cavity travels about 1,000 kilometers, a large fraction of the United States within our 16-meter volume or length. And this plot at the bottom shows that we inject squeezing into our system, say anti-squeezing, we see it rotate down into squeezing. And when we inject squeezing, we see it rotate into anti-squeezing. And at intermediate angles, we see intermediate rotations. This black curve is the quantum advantage that you would get if you plugged this system directly into LIGO. And of course, ideally, we would see this black curve go below the 0 dB line everywhere, but the limitations of a 16-meter cavity, losses in particular, prevent us from being able to do that. So now the point is, we've demonstrated, we actually learned quite a bit about some of the control and integration requirements for doing this. And now we intend to install such a cavity on advanced LIGO, a 300-meter filter cavity, which you can sort of see running along one of the arms, punching through one of the vacuum chambers. And ultimately, we want to achieve 6 dB of frequency dependent squeezing. We intend to have this system operating, although perhaps only at 4.5 dB in the next observing run. And at least the quantum noise can become sub-SQL while we are observing. We're still working on the instrument. We, of course, would love the instrument to be fully itself sub-SQL, but that's yet more improvements at low frequencies, which is quite a challenge. But we've drawn on a lot of design knowledge, both from these experiments and the interferometer itself. Basically, anytime you connect something to LIGO, the most likely thing that you'll do is degrade its sensitivity. So you have to do a lot of engineering in order to prevent that. And this 300-meter cavity is designed specifically for it. And it's also long. This 300 meters is long because optical losses, the way squeeze states degrade, have a favorable scaling with the length of the cavity, hence 16 meters to 300 meters. So what we hope to achieve in the next, not the next observing run, but in the next few observing runs is this red curve, which also requires improving the coding thermal noise. But ultimately, if we do both of those things and continue to work on the low frequency noise, we can create a detector that continuously runs sub SQL and reaches 300 megaparsecs, over 300 megaparsecs for binary neutron stars, and 2,500 for binary black holes. And so, at least for the next observing run, the other thing, in order to reach a noise curve that impressive, the work that it takes to get there is also to improve the degradation or decrease the degradations of the squeeze states. This is where, the point I'm making here is that while squeezing has been done in university labs for quite some time, we're still learning a number of things about how it behaves when you attach it to real detectors like advanced LIGO that are far more complex and have a wider range of ways to degrade the squeeze states. And in 03, some further analysis of data at both sites shows that the losses in squeezing are in fact intrinsically frequency dependent, and it lets you pull out some otherwise hidden parameters of the interferometer. And the way to improve these things is actually improving various mode matching. And independently, people have worked on both decreasing losses in core components such as Faraday isolators that have not intrinsic loss, but loss that's difficult to get around due to various polarizing elements. And we're using active wavefront control to perfectly match the beam between various cavities in our interferometer in order to mitigate these various degradations that we've observed. And in fact, I was at LIGO Hanford last week working on commissioning. These are very fresh pictures of what it looks like in the chamber where frequency dependent squeezing will be installed. Here's a triple suspension for one of the filter cavity mirrors. Here are 2 double suspensions which hold these active wavefront control optics, where a very large piezo actually goes through a special mechanical element that bends the mirrors in a controlled fashion so that we can optimally match our squeezing to our interferometer. And here is this is the OPO, and here are all of the optics and fibers and Faraday isolators, super low loss Faraday isolators that relay the beams around to prepare them into the state ready for the interferometer. And the reason why all of these things are on, this is an active inertial table that's substantially better than ambient seismic environment. And these are suspensions yet on top of that table. And the reason is that even though squeeze light is supposed to be dark, a tiny bit of interferometer likely leaks over to this system, and it's enough to ruin all of what you would gain by squeezing unless you make it very low noise. So finally, that gives a good overview of what we're doing in this near term with O3 in terms of the quantum noise improvements, frequency dependent squeezing. But going back to this final stretch of astrophysics that we would like to get, that LIGO is within, at least for binary black holes, a factor of 10 of the Hubble distance. Various groups are planning next generations of gravitational wave detectors, generally making them longer to improve their reach, but also improving the underlying technologies where they can, and using some things that we've learned, number of things that we've learned with LIGO to create these purple and green curves, Einstein Telescope and Cosmic Explorer being the US-led design, a design that's more appropriate for US infrastructure. In fact, that's a 40-kilometer observatory, 10 times more optical power, 10 dB of squeezing in the nominal design, going to even lower frequencies using heavier and larger suspensions. And it will have very high event rates because of this additional factor of 10 in range that it can see. And then the events that we currently see will have a factor of approximately 10 higher signal to noise, which will give us greater insights into the actual physics going on in general relativity and in nuclear matter. When we make observations, they actually, this signal to noise is of a level that actually stresses numerical relativity's ability to simulate these events. And so a remarkable amount of science will become available with these next generation detectors if we can get them through. And then on the right here is a plot of what the reach looks like versus the population that you expect across cosmic time. In fact, at its nominal design sensitivity, it captures every event in the universe essentially. So these are incredibly impressive next generation devices. And you should look up a horizon study that solicits everyone's support, particularly astronomers, towards the science case and the design goals of these detectors. And you can find out more at cosmicexplorer.org. So thank you. To wrap up, to say we've now integrated quantum squeezing, not just as a demonstration, but to actually improve our event rate and improve the signal to noise of the events that we see. We're still learning about squeezing in these at scale implementations with the detector. Some of these things I've written up. And in the meantime, we've used our detector to show some results of very macroscopic quantum objects, the test masses, which are 40 kilograms at room temperature, that they are behaving, certainly as we expect, but at a rather remarkable scale. And our future designs to actually use our observations and our understanding of the quantum noise in these detectors to violate a seemingly fundamental Heisenberg uncertainty in just how sensitively we are probing these test masses with our gravitational wave interferometers. So thank you.
Great, thanks, Lee. That's an excellent talk. So with that, I guess we can open it up to questions. Are there any questions either here in person or over Zoom?
Yeah, I got a couple of questions. I mean, just that general question, not about the squeezing, but just about the instrument. If at room temperature, is that optimal?
If they're at room temperature, is that what?
I mean, if you could cool the mirrors, would you?
Yes. So that's a good question. So what do you benefit by cooling it? So in terms of the thermal noise, the majority of the thermal noise from the suspensions themselves is already small enough to not be an issue. The coating thermal noise very likely improves if you can cool the mirrors. And that's mainly it. So there's not a massive advantage in cooling them. I've moved too far, sorry. I was going to go back to the noise budget. There's not a massive advantage in cooling them. Although we're now, since we are starting to hit upon the limits of coating thermal noise, our avenue is mostly to improve the material properties rather than cool them, because it's quite difficult to cool something that has a megawatt on it that cannot touch anything. You can only use radiative cooling. And so in fact, fused silica is not a useful material. If you want cryogenic suspensions, you need to use crystalline materials. And there are detector designs to do that. The CE design originally was a cryogenic one. The Voyager design, which is a proposed upgrade to LIGO, is to transition into silicon optics. And yes, especially at low frequencies, it gains a decent bit by having the colder test masses. But it's actually it's a fairly subtle discussion, as it turns out, on what the benefits are for cooling to cryogenic temperatures. So here you can see that you would benefit more from just increasing the mass of the test masses than cooling, because this is all the thermal noise from the suspension, and you would benefit from just increasing the beam size to lower this red curve. Of course, we're at the limits of what we can do with our facilities. We can't increase the beam size more, but to cool them, you have to do even more dramatic changes, such as change to silicon optics. So kind of a wondering answer, sorry, but.
That was interesting, thanks.
Okay, so we have a few questions on Zoom. So Lee, you have a question?
Hi. Yeah, I was thinking about future space-based gravitational waves. I know they're looking at lower frequencies, I think. So do you think the squeezing will play a role in those as well?
No, and kind of in no circumstance can it. And the reason for this is that they gain all of their sensitivity using extremely long baselines. That's also why they're lower frequency, like millihertz, to hundreds of millihertz. And the reason why I say that they will not benefit from squeezing is that they simply cannot have mirrors that are large enough to collect all of the light between two of their test mass units, their spacecraft. Like they don't have just the diffraction limit. They lose, I don't know what it is, but it's almost all of the light. And it just turns out that, yes, that's not great for quantum noise, but they gain so much from the long baseline in terms of strain sensitivity that it's okay with losing a ton of photons. The consequence of this is that the losses are 100% and no squeeze state will ever be preserved. So yeah, it will simply always be too lossy to do squeezing in space. Love to be proven wrong, but it seems rather fundamental from my perspective. You would need a very, very large mirrors to pull it off.
Okay. Raghav, I think your question's next.
Yeah, thank you. So this is a fantastic talk, Lee. So I really learned quite a bit during your talk. So I had a question on the rates. So you showed that, kind of advancing the precision, you kind of detect more events, so to speak, as a function of days during your runtime. You had this chart that basically blew up when you go to 03.
Yes.
Right. So is there a limit coming from that point of view? So I come from high energy experiment. So there we have a fundamental limit on our event rate, right? It's basically in our readouts. So is there some point, because you're doing the squeezing and you have to build these states in order to calculate the exact time and the rates and everything, is there going to be a ceiling to this curve depending on the precision that you want?
So, I mean, other than that, we will just max out the detector this generation with upgrades detector at these levels. If you take 140 megaparsecs and you go to 225, that's a factor of 2. So, we'll get another factor of 10 perhaps here. So there's no fundamental limit in terms of anything with the readout or the detector. In fact, it might even be favorable because the ratio of events to glitches improves. So, so it actually might improve various event statistics simply to have a higher rate. But what you will hit, and this is actually really just a concern for the 3rd generation detectors, and it's of course a very fundamental concern for the space-based detectors, is that at some point your event rate becomes so large that to see single events, you have to fit multiple events. And I mean, that's not fundamental. That's just the computing infrastructure to do the data analysis gets substantially more complex, and it might degrade some events in some circumstances due to, uncertainty from one event overlapping into the other. But yeah. I don't think, even at the 3rd generation event rates, I don't think there's going to be like every event's going to have overlap with another event. I think it's just going to happen at kind of the, enough that you need to keep it in your pipeline, but not so much that it's like a truly fundamental issue. Whereas for the space-based detectors, if you're measuring a millihertz, it takes a year and you're seeing everything in that year. So you have to do a simultaneous fit of every event at all time to get anything.
Yeah, a lot of this is just mind-boggling, but yeah, thanks for your talk. Very nice. Some
of that also applies to like the nanograv kind of results. Their fitting is also requires, you're disentangling many things at once.
All right, I think next is Dave.
Yeah, thanks, Lee, for the really great talk. So, so it's great to see you already putting in this long filter cavity, and I guess you're aiming for 6 dB in the near term. I guess I was a little surprised that in this even blue sky Cosmic Explorer, you're only going to 10 dB, and I know only there in quotes because I know it's extremely hard. But given an order of magnitude increase in the facility size and everything, I mean, so what is the practical limit that gets you stopped at 10 dB there, or can you imagine really even going farther?
Yeah, I mean, 10 dB is like, it's a reach, but it's like a feasible reach that suits a proposal well. Obviously, if we can get higher, then we would. But here's where it comes down to To get 10 dB, you need losses that are below 7%, not 10% as it turns out, 7% because we can only inject about 15 dB of squeezing. And that's because when we use a filter cavity, the tiny bit of residual loss in the filter cavity actually causes dephasing, what is essentially phase noise of the squeeze state. That sets an optimal squeezing level to inject of around 14 dB. And then the question is, how much loss is acceptable before you at 14 dB to hit 10 dB? And it turns out it's only 7%. And at least with current technology, we get about 1% per pass for a Faraday. And that adds up pretty quickly because we need currently 5 passes when we use a filter cavity. Obviously, you know, by the future, we can probably get that down to maybe 2 or something if we're really, really good and do some additional engineering. So that's 2 passes there. That's maybe 2%. Our OPO is 1 to 2% intrinsic loss due to our cavity enhancements. Maybe we can improve it to get it down to 1. So now we're talking 3 or 4%. And then it's how good is the mode matching given, you know, even more power in the arms, changing the mode, detuning it, whatever. And then our output mode cleaner will have a little bit of loss. So like, it's hard to envision us being substantially below 5% of loss, just given the number of elements that you have to engineer into a detector that's sensitive at acoustic frequencies. Now, like all these Faradays are only necessary because we're at acoustic frequencies. You can throw them all away or do something different if you're doing things even above a kilohertz. And that would help a lot. And then if you can get rid of mode cleaners and stuff, that helps a lot. So like, yeah, 10 dB is kind of a limit just because of a lot of technical limits. And it's also, you know, ambitious, but not crazily ambitious for a future proposal kind of level.
Okay,
Yep.
I see. Yeah, thanks.
But I mean, the most anyone has ever gotten is, you know, about 15 dB. So with an optical state.
Yeah, I guess, you know, you guys are really just pushing technology on so many fronts. I mean, I appreciate everything you said. I'm just, you know, the amount of investment in some of the other technologies, it seems a little unfortunate to us outside that things like Faraday isolators and stuff are, you know, just seems like throwing enough money at those things, you could push them down, but I know nothing's easy.
Yes, and that is kind of it, is just to engineer one of these that meets our specs in the first place is challenging, and then to add on the little bit of extra to get it lower loss is challenging, and doing, you know, pushing the limits just will take time. And it's feasible that we can do more than 10 dB, but it's hard to promise at this stage. Of course,
Thanks.
anything could happen in 20 years.
Yeah. No, looking
And
forward to it.
lots of people expect lots of things to happen. So in the quantum realm, so.
All right, great. Any last minute questions? Okay, if not, then thank you again, Leo. It was an excellent talk. And thank you for everyone calling in, and